So as we were saying, our area for the section 3, let's quickly verify it and then let's proceed. So that was 1963.75. So let's put it over here, 1963.75. Okay. Someone should quickly punch this. Someone should quickly punch this and tell me the answer. Someone should quickly punch all of this. That is, if you can punch it very well, you are going to get the answer. But if you are unable to punch it very well, it also becomes a major problem or a major challenge. Okay. So someone should quickly punch this and tell me the answer. Better still, we can all do it together. That is 35,000 over 2.1 times 10 exponent, let's say 5. You can shift your cursor, bring your multiplication sign, open another bracket, and you begin the divisions in it again, okay? That is 200 over 314.2. You can shift cursor and bring your addition sign, open a different division sign. That is 250 over 706.95. From there, what do? We add the last one, that is 220. 220 all over 1963.75. Finally, what are we going to get? What are we going to get? You can punch your answers in the comment section. I'm going to verify that and tell you. No, 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 no. Daniel, please quickly check your answer again. So you are supposed to get 0.18, let me say 37. Okay, let's just maintain 4 decimal places. Okay, that is Newton. Oh, no, no, not Newton. Because it's extension, it becomes millimeters. Okay. So this is millimeters. It becomes millimeters. So we are done solving the problem. We are done solving this problem. We are done solving this problem. Okay. Let's also go and see if we can also touch on a different problem to play with. But before that, is anyone having any question to ask? Any question to ask before we proceed? Any question before we proceed? Okay, if no one is having any question for me, then I want to ask the whole class a question. Can anyone tell me the difference between prismatic and non-prismatic section? Can anyone tell me the difference between prismatic and non-prismatic section? Hello? Anyone to tell me to make us history? Okay, here we are. Please kindly unmute yourself and make us history.
Okay, good evening, sir.
Evening, sir. How are you?
I'm fine, sir. So with the prismatic sections, they have uniform cross sections throughout, but the non-prismatic ones they have varying cross section.
Thank you very much. That was a contribution. So I think that was exactly what I said. Okay. I said prismatic sections has uniform cross-sectional areas and non-prismatic section has a varying cross-section. Okay. So that was exactly what I said. Let's quickly pick a different question and see how history we can all become. Okay. Is there anyone having any question to ask before we proceed? Any question to ask before we proceed? Okay, if there will be no question, then let's proceed to see if we can get any other question to solve. Okay, this question was just like the one we solved. Let's pick a question that is a bit more technical. Okay, so let's hit on this a bit. So let's look at bars with varying axial loads. Okay, the first one we saw are bars with what? The same load on them. Okay, let's also solve one question on bars with varying axial loads. Take note that bars with varying axial loads indicate that the axial load at the end of the bars are not the same or varying uh, loads, okay, have. Or better still, even before this, let's say that, look at this question over here. Look at this question over here. This problem 3.2 says that a member, a member formed by connecting a steel bar to an aluminum bar is shown in the figure below. Assuming that the bars are prevented from buckling sideways, calculate the magnitude force P that will cause the total length of the member to decrease by 0.25. So you see that they've given you the total change in length. So you are now supposed to calculate for the P. Okay, it's just a change of subject. The value of elastic modulus of the aluminum is given as this, and that of, let me say, the other material is also given as this. So you see over here is different kind of elasticities that is being provided over here. Okay. So first of all, the area of the bar was being calculated for, and also the area of the aluminum bar was also being calculated for. Okay. You can see the way this one is. It's not a round. It is let me say a square one. So they just use length times breadth to get for the hot area. Okay. Uh-huh. You know that our change in length, this was our general rule we are talking about, but the change in length of one member can be expressed as that. The change in length of the other member can also be expressed as that. Okay. At the end of the day, because the P is going to be the same, it has been substituted out. Okay. So by substitution, if you make P the subject, you realize that you would have been able to get a P. It's not anything too difficult. Okay. Uh-huh. The one I want us to look at, particularly, is this one's going. Okay. That is the axially loaded bars with varying loads. Okay. Now we can continue. Bars with varying axial load indicate that the axial load at the end of the bar are not the same, or varying load have been applied along the section of the member. Take note that such members must first be in equilibrium. That is, sum of all the forces in the direction x or y must be zero. That is f of x is equal to 0, or let me say the sum of f of x is equal to 0 and sum of f of y is also equal to 0 respectively. Problem of this nature generally require the use of superposition method. Note that free body diagram must also be in equilibrium. Yes, it is important to know that after balancing the forces, each segment will either be in tension or compression and must be in what? Equilibrium. No matter how you split them into tension and, let me say, compression forces, they should still be in equilibrium. If we say something is in equilibrium, the thing is actually stable. Yes, if we say something is in equilibrium, it means that the thing is stable. Uh-huh. Also, the extension of each segment, or let me say part one, can now be calculated. Similarly, the stress and strain of each part can now be calculated. Take note that the total extension is the algebraic sum of the deformation of the separate segments. Okay, and these are some steps to follow in order to be able to calculate for some of these problems. Okay, so you can see that these bars they have what? Varying loads. So how can we be able to what? Crack this to be able to solve? Look at the question over here. A brass bar. You see that this is a brass, so at the end of the day, the elasticity is also different. It's no more 2.1, you see, times 10 exponent 5. But in this case, it is what? The elasticity is what? 1.05 times 10. You should be taking note of some of these things. Yes, you should be taking note of some of these things. So let's proceed. A brass bar having cross-sectional area of, let me say, they've given you the area of 1,000 millimeters squared is subjected to an axial is subjected to axial force as shown in the figure below. Find the total extension of the bar. If the E is being given as this, if E is being given as this. Before we proceed with the question, I want somebody to read the question for me one last more time before we proceed. Anyone, any volunteer to read the question for us one last more time before we proceed? Any volunteer to read the
Yes,
question for us one last more time before we proceed?
yes, please.
Okay. So please, you can
It
take.
says a brass bar having a cross-sectional area of 1,000 millimeters square is subjected to axial force as shown in the figure below. Find the total extension of the bar. Take E is equal to 1.05 times 10 raised to the power 5 Newton per millimeter squared.
Okay, thank you very much. Thank you very much. So look at what is happening over here. You can see that over here, the arrow is moving away, showing like it's in tension. But if you come and look at over here too, it is showing like, this person is in compression. So to be able to solve this work very, very, very well, first of all, you have to know how to be able to what? Break this into various sections. Okay. Then from there, you can now continue to solve. Okay. I could have just flipped to, let me say, an empty screen for us to solve. But first of all, let's analyze the question over here. Okay. Let's analyze the question over here first, even before we go and start to solve somewhere else. Okay. So this should tell us that first of all, we are going to be having, let me say, 3 boxes. Okay. So look at me drawing 3 boxes over here. This is my first box. One. Let me put the other one over here. 2. You see. Then I can put the last one over here. Let me put the last one over here. 3. So now you see what I've done. So this is AB. This is AB. And now let's say that this is BC. And now this is the CD. You see how I've split it? Exactly. Exactly. So now let's solve from what? Left to right. Now we can now solve from what? Left to right. So the first one, what can you see? You can see that this one is in what? This one is in tension, right? So you maintain tension for both sides. Samuel, if I catch you writing on my screen again, I'll remove you from the class and you will not be able to join again. So this one is in what? Tension. Okay. So 50. First of all, let's even write the 50 down. So this is 50 Newton. This is 50 kilonewton. 50 kilonewton. As you are seeing over here. So the other place, what are we going to do? What can we put over there? But you see that over here, we can't see any 50 over here. So at the end of the day, now we are now becoming confused. Don't get confused. You see, in physics, that is under a topic known as vectors. You will learn that when forces are moving in the same direction and we want to get their resultant vector, we add them. But when they are moving in opposite direction, you do what? You subtract them. Do you understand me? So look at over here. What is happening over here? These two forces, what is happening to them? These two forces over here, what is happening to them? You realize that this one is moving in this direction. This one is also moving in this what? Direction. So what do we have to do? We have to subtract them. We have to what? Subtract them. Okay. We have to subtract them. So at the end of the day, to be able to know the force, we have to subtract the 20 from what? 80, because 20 and 80, they are moving in opposite direction. They are moving in opposite direction. If you don't want to use the 20 and this one too, you can do it the other way around. If you still want to know the force at B, then it also means that you can also what? Since look at the 50 and the 80 are also moving in opposite direction. Okay. So if the 50 and the 80 are also moving in opposite direction, then what should I tell you? This kind of questions, you don't even have to even think plenty. It is just as simple as that. It is logic. First of all, you can even compare the end ones. Look at the first one. This one shows that this one, the AB. So you see the AB that I have drawn. You ask this one, outer one is in 50. It's in tension. It means that the whole of this is in hot tension. So if this one is 50 kilonewton, this one is also going to be hot, 50 kilonewton. Okay, let's go and talk about the other one too. Let's come and talk about this one, even before I talk about the middle one. This one too, as this one is in compression, it should tell you that you see that over here, you see that this is 10 and it is showing that this is in compression. So the other one will also be so if here is 10 Newton, here will also be what? 10 Newton. Now when we are done, we come and focus on the middle one and I'll show you something. So this is 10 kilonewton. This one was also what? 10 kilonewton. Exactly. You see what you are seeing over here. So the middle one, how do we get them? Because at the end of the day, they are moving in opposite direction. You see, And the direction is also showing that it is pointing inward. So let's maintain that direction. Since they are moving in opposite direction, 20, or let me say 80 minus 20, what are you going to get? You're going to get 50. 80 minus 20, you're going to get what? 50. Let's come to CD. You see that this 10 and this 20, they are moving in the same direction. Look at this 10. This 10 over here, this 10 over here, and this 20, they are also moving in the what? Same direction. So if I want to get a force at C, what do? I'll just add the 20 plus 10 will give us what? It's not 30. I'll use a different color pen to write it. So I'm going to write what? 30 over here. So this becomes 30 what? Kilonewton. 30 kilonewton. You see, as I've gotten an answer like that, it is very, very beautiful. If I want to also get a force at B, it is two things. I can either subtract, you see that the 50 and then the 80, they are moving in opposite direction. You see, so I can either choose to subtract the 50 from 80, I'll still get my 30 over here. You see, so it is as simple as that. It is as simple as that. It is as simple as that. So over here, before we even proceed, I want to take some few questions from you before we proceed. Do you understand, or there was something that was challenging you? Was there anything you didn't understand? Was there anything you didn't understand, or is there anything you wish I could throw more light on before we proceed to solve the work? All right. So as I was saying, in physics, if bodies are moving in the same direction and we want to get their resultant vector, we add them. But if they are moving in opposite direction, you subtract. Okay. As I said, AB, this first diagram, this one should tell you that this is in tension. So if you put 50 over here, you also put 50 over here this side. Come and consider the last one, CD. You see that here it's showing that it is in what? Compression. So if here is 10 Newton, here also be 10 Newton. Now if you want to get the BC, the forces at BC, what are we going to do? Now let's compare the force at what? A and B to get the force at B. Okay, so you see that at A, we have 50 kilonewton moving to the what? Moving outside the bar. Okay. And at B, we have 80 Newton also moving outward. So you see that they are all moving in different directions. So we just have to what? Subtract them to get the force at B. Compare the CD. And if you subtract the 80 from 50 from 80, you're going to get 30. If you come and compare the force at C to get the force at C, look at this 10 Newton and the 20. They are moving in the same direction. So we just add it. 20 plus 10 is what? 30. That's why I'm having 30 Newton. Once you're able to get this, at the end of the day, you can just solve your work and you are good to go. Take note, before I continue to solve the work, take note that for bodies, okay, for bodies that are in tension, they are hot, always positive. Okay, but the ones that are in compression are always hot, negative. Okay, if you see that your body is in compression, it is negative. Okay, but for the ones that are in tension, we consider them to be hot, positive, because at the end of the day, there will be an increase in length. Okay, but the compression shows that there will be a decrease in length. Okay, that is why at the end of the day they are being negative. So let's just proceed to solve our work. Our question says we should calculate what the total extension of the bar. Total extension. So let's just go to given quick, and let's make history. So this is our problem 3.3. Okay, problem 3.3. So problem 3.3. So let's solve problem 3.3. Over here, I write problem 3.3, then my given follows. So this is the problem 3.3. Problem 3.3. So let's start from the given, and this becomes our given. Now we can put down our important details and solve the work. We are good to go. We are good to go. So first of all, a bar having a cross-sectional area of That is all the area is okay, 1,000 millimeters squared. So cross-sectional area. So the area is equal to 1,000 millimeters squared. 1,000 millimeter squared. Okay, and that is our area. Also, what other thing else can we figure out? They say we should calculate for the total extension of the bar. So the total extension of the bar, the total extension, the total extension, which we don't know, so we are just going to put the question mark over there. So the total extension is also known as the total elongation or total change in length. So I'm going to denote it as this, which is equal to what? We don't know, so we put question mark over there. Now my Young modulus, you see, they say we should take the E, the Young's modulus, the Young's modulus. So we should take the Young's modulus, take the Young modulus. So we should take the Young modulus to be equal to E, which is equal to 1.05 times 10 exponent 5, 1.05. So that is 1.05 times 10 exponent 5 Newton per millimeter squared. So that is our Young's modulus. Okay. From here, we can now solve our question. Let's quickly put our problem down to make life much more easier. Since we have already analyzed it over here, we just pick it bit by bit and represent it on our diagram or board. We are good to go. So this is the first one. And this is AB. This is our AB. We saw that the AB was in tension. So this was the 50 kilonewton. 50 kilonewton. Or let me say 50 times 10 exponent 3. 50 times 10 exponent 3 Newton. Now let me draw a different one and name it BC. So this one was in compression. This one is also in compression. So you see this one was 30, 30. As we are seeing over here, you see. So this one was 30 kilonewton. 30 kilonewton. And this also became the 30 kilonewton. You see. So we can now draw the last one. Look at how the last one look like. You can also draw the last one. The last one was also in hot compression. You see. So this one was also 10 kilonewton, which is the same as 10 times 10 exponent 3 Newton. You see, this one was also 10 exponent 3 Newton. Or let's say 10 kilonewton. So since these two are in compression, we classify them as what? Negative. Okay, because they are going to decrease. They are going to decrease at the end of the day. Okay, but this one is going to increase if they stretch it. So it's going to become positive. You see. So we can proceed to solve our work. We can proceed to solve our work. Let's come back to the question one last more time again. The question is now asking us to calculate for our total change in length. We can even take it bit by bit. We can pick the first one, calculate for each change in length. We can pick for the second one. If you finish, we come and add all. Okay. So look at the solution. This is our solution. But before that, let's calibrate it, okay, to avoid any kind of uncertainty. So this is BC, and this become our hot CD, so that it doesn't confuse you much. It doesn't confuse you much. Okay. The question we had, if you like, I can put the question over here. You have the question, okay? So this is the question over here that we are solving. So it shouldn't be much of your. There will be no need for me to still write the question down. So let's proceed. Let's proceed. So our solution, they say we should calculate for our total change in length. But we know that the total change in length, the formula of the total change in length is given as this. So the total change in length in this case, the formula is going to be given as this. Look at the first AB. That is the change in length of AB, okay, plus change in length of BC plus that. But in this case, AB is in tension, and then the rest are what? The rest are in compression. So this is how our formula is going to look like. So the first one is going to be what? Change in length, total change in length of the section one, okay, plus. Now because this one is in what? Compression, I bring negative. Total change in length of the section 2, okay, then plus. Then another one that I bring the negative what? Change in length of the third one too, okay, because of the nature of the compression that we are seeing over there. That is what is bringing about all that. See, so from this background knowledge, we can just solve our work and then we are good to go. We can solve our work and then we are good to go. So we can even choose to take it bit by bit to make life easier. Take note that this first one is just AB. This one is AB. This one is what? BC. And this one is what? CD. So if you like, this time we can take it step by step. So let's do for change in length of what? Of AB. If you like, we can do it step by. If you like to, we can just solve all together like that. If you like to, we can just solve all together like that. Their A has been provided to be 1,000. Okay, the A of them has been provided to be 1,000. If you like to, we can just substitute it like that and we are good to go. So if you like to, let's just compute all and see how that one too can be done. So our total change in length is equal to what? Now we are going to just open, let's say, so this is the first one. So as we all know, the formula PL over what? AE over AE. But in this case, you see, it's not just going to be anyone, no, but we have to be specific, okay? Because in this case, we have so many P's. Because in this case, we have so many P, okay? So let's proceed. But look at the dimensions that was used for their length. Look at the dimension that was used for their length. This one is 600 what? This one is 600 millimeters, and this one is 1 meter. This one became what? 1.20 meter. Okay. So let's quickly write the length under them, and then let's now proceed with the work. Okay. So the length of this one was 600 millimeters. See, this one is 600 millimeters. And this one too this one is also, let's say, we just multiplied by 1,000, okay? So let's just say 1.0 times 10 exponent 3. Don't get confused, it is still the same thing. Let's represent it by this millimeters, okay? Because you know that 1 millimeter is equal to what? You know that 1,000 millimeters give 1 meter, right? So if 1 meter, you want to convert it into millimeters, it's just a matter of 1,000. Okay. So let me just write 1,000 millimeters over there. 1, 2, 3. So over here to the last one, what can we write? You see that this is what? 1.20. So if you multiply it by 1,000, what are you going to get? How are you going to get? Multiply 1.20 times 1,000 and tell me the answer. You're going to get 1,200. So this become 1,200. 1,200 millimeters. 1,200 millimeters. So let's all do it quickly and nicely. Uh-huh. So as we are done like this, now we can proceed with our work. So you see this is L1, P1. The area has been given already, and we know that it is equal for all. The E has also been given. We know how it is also equal for all. So let's proceed. And this one, now in place of the plus, what am I going to bring? And I can now bring the negative what minus what? PL. You see. So minus P multiplying the L. But in this case, it becomes P2 times L2. All over what? The area times the E. You see. Over here too, because of the negative sign, it's going to become minus what? P, let's say P3, L3, multiplying what? A, E. Okay. Since they all have the same area and the same elasticity, then let's substitute that one out, and at the end of the day, to make our work much more easier. Okay. So in substituting the area, and then let me say uh, elasticity out, is going to give us a relation such as what? 1 over what? AE. 1 over AE. Okay. Now multiplying, let's say, everything in this bracket. So we can say that what? PL. PL is P1 multiplying the what? L1. Okay. Minus P2 multiplying the L2. Okay. Minus the P3 multiplying L3. So let's all quickly do this together, and let's see the answer you're going to get. Quickly, quickly, quickly. Who is done? Who is done? Who is done? Who is done? So this one is 1 over what? The A. For the A, what did we get for the A? We know that it is 1,000 for all, right? So it is 1,000, let's say 1,000 millimeters squared times 1.05 times 10 exponent 5. Okay, since that is the elasticity, so times 10 exponent